welcome back. I had to use that. I had to stop recording video because of the application issue. So, coming back to the advantages of resource models, the data is persisted, and hence this can be used for recovering in case of any failures. Any failures. It also allows for asynchronous computation in the peer-to-peer model, where synchronous communication between tasks means that virtual machines must be kept running until all the child tasks have been received the corresponding data. If at all virtual machines have been stopped before the childs have been the child tasks have been have received the data, so it will be a issue, and there will be a no optimization. So this increases the resource utilization, but also decrease the cost of virtual machine leasing. And also to avoid the communication and processing overheads, as well as the virtual machine provisioning and reprovisioning delays, tasks in the pipeline are clustered together and are always assigned to run on the same virtual machine. And there are several few advantages. Again, so when it comes to implementation of the algorithm, before implementation, I would like to talk about the overview and the motivation a bit. Here, this algorithm allows us to adapt to unexpected delays caused by poor estimates or by environmental changes such as performance variation, network congestion, network failure, and VM provisioning delays, etc. The purpose is to find the balance between the local knowledge of dynamic algorithms and the global knowledge of static algorithms. To achieve this, we use the concept of pipeline, and by statically scheduling all the tasks in the execution queue at once. Pipeline, here the pipeline are used is a common topological structure in scientific workflows, and is simply a group of tasks with one-to-one sequential relationship between them. Pipeline P is defined as a set of tasks with where there is an edge ei to I plus 1 between task Ti and task Ti plus 1. In other words, T1 is the parent of T2 and T2 is the parent of T3, and so on. Here the first task in a pipeline may have more than one parent, but it must have only one child task. All other tasks must have a single parent and one child. I'll be explaining this in the further slides in a much better way. So when it comes to a pipeline, there's a pictorial representation of the pipeline here, where the pictorial representation gives the first one is the first pictorial representation, that is the data aggregation, is composed of all tasks of type 1, and the second one of all types tasks of type 4, that is in the data distribution. Scheduling these bag of tasks is much simpler than scheduling a workflow. Here there are no dependencies, the tasks are homogeneous and have to finish at the same time. So we model the problem of running these tasks before their deadline and with minimum cost as a variation of the unbounded knapsack problem, and to find an optimal solution using dynamic programming. So when it comes to the working of the pipeline here, the task 1 there are several tasks. As I mentioned, the first task in the pipeline may have more than one parent, but it must have only one child. So the task 2 is having only is the child of task 1, that is the task 2 is having more than one parent. So all the tasks data from the task 1 is been aggregated to the task type 2, which is the input for task type 2, and in turn it is the input for the task 3, that is the child of task 2. Here the data is distributed again for the task type 4. Again all these data are parallelly distributed, and again they consolidate and aggregate the data and give the input to the task type 5. So there are several advantages from the pipeline here. The tasks are sequential and are required to run one after the other. There is no benefit in terms of parallelization on assigning them to different virtual machines, but the output file of a task becomes the input file of the next one, as I already told, by running on the same virtual machine, so that we can avoid the uh, cost, avoid spending more on the price and the time of transferring these files in and out of the global storage. So we use a couple of problems in the WRSPS algorithm, where this problem, the one is the unbounded knapsack problem. This problem can be solved optimally using dynamic programming by considering knapsacks of smaller capacities as sub problems and storing the best value of each capacity. So here the smaller capacities of all sub problems have been considered one at a time, and the values have been stored. I mean, the best value out of the sub problems have been stored in each capacity, so that it is optimally using the algorithm, and there is no time consumption or and which results in the expenses. So there are a couple of algorithms in which tasks are first sorted in topological order. In this way, we can ensure that the dependencies are preserved, and for each sorted task that has not been processed, the algorithm recursively tries to build a pipeline that starts with the task. Performance evaluation. There are again two types of evaluation done. First one is provisioning static scheduling algorithm. This algorithm assigns sub deadlines to tasks that like it assigns the deadlines for each and every task here, and schedules them onto existing or the newly released virtual machines, so that the cost is minimized. It was designed to schedule a group of interrelated workflows, but it can easily be adapted to schedule a single one. It was chosen as it is a static algorithm capable of generating high quality solutions. Its drawback is its inability to meet deadlines when unexpected delay occurs, such as network network connectivity issues. The second type of evaluation is SES. This dynamic algorithm that has an auto scaling mechanism that allocates and deallocates VM based on the current status of works tasks. It determines the most cost efficient VM type for each task and creates a load vector, so that here it determines a virtual machine type every time, so that it can create a load vector. This load vector is updated every scheduling cycle and indicates how many virtual machines of each type have been needed for the in order to finish the finish the execution or the workflow well within the time, which also minimizes the cost. The purpose is to demonstrate how the static component of WRPS allows is to produce better quality schedules than SES. Conclusion: WRS is used in clouds, which for scientific workflows, used for executing the scientific workflows for in clouds, which is capable of generating high quality schedules. From this we also know that it minimizes the overall cost of using the cloud infrastructure while meeting a user defined deadline. It also has a static component that allows it to find the optimal schedule for a group of workflows. The simulation experiments show that our solution has an overall better performance than the state of art algorithms. It is also successful in meeting deadlines under unpredictable situations, such as involving performance variation, network congestion, network connectivity issues, inaccurate task estimations, etc. So this is it. Thank you. Thanks a lot.